Hello, my name is Benjamin Setterholm. I'm a PhD candidate at the University of Michigan. And today I'll talk about looking at a particular Herbig disk, inner disk, to look for temporal changes. So to date, in order to examine disk structure and to get enough UV coverage with near-infrared interferometry, it required several nights of data at VLTI to move the auxiliary telescopes to different positions, and with previous generation Chara instrumentation only allowing several baselines at a time. So in order to fill up the UV plane enough to have information to start pulling out structural information inside of disks, you would need to conduct observations typically over the course of weeks or months and sometimes years. And so the key assumption when you're doing the looking for structure in the disk then is that the inner disk is static, because if it's changing underneath, then you can't make out the individual features. However, we see that for many young stellar object sources, there are brightness fluctuations on the orders of days, weeks, and months. And we see in scattered light images of the large-scale structure of the disk, shadows that sometimes move over the course of time, indicating that there is something in the inner disk that is changing temporally. And then finally, if you just consider the orbital timescale at the astrosilicate dust sublimation radius, you have an entire orbit typically on the order of a month or so for these sources. And so if you are conducting observations over the course of several months and combining them together, you've smeared out any sort of orbital signature many times over. So what I've done is I've looked at a more high cadence observation study of the Herbig Ae disk HD 163296, which is a popular source, mostly because it is close by at 100 parsecs away. So 10 milliarc seconds is 1 AU on inner disk scale. So it's a prime target to look at with today's near infrared interferometry facilities. And so we can see from ALMA data that the central source, kinematically the central source is about 2 solar masses, and that the entire disk is orbiting clockwise. So just to kind of give the orientation of the outer disk here, seen in scattered light, the northeast side is the side that's closest to us, and then the southwest is the far side of the disk, orbiting clockwise. If you look in the previous literature, taking these observations of this disk spanning sometimes as short as 2 months here and sometimes as long as 10 years, collecting all this data, you see some general features of this disk. Most notably, all of these studies, the first in K-band, but the rest of them are all showing in H-band, all of these studies show that the disk is oriented together with the outer disk. So there isn't a misalignment between the inner and outer disk. And secondly, these studies all provide a similar sort of size scale for the disk and show much of the emission seeming to come from within the dust sublimation radius, which is the green dotted line here on the far right diagram. And so for all of these images, I'm showing all of these models to scale to each other, and then on the bottom, the UV coverage that was used also to scale with each other to get these models. And so here I examine a new data set. So I've collected data with the Chara array with the Mercax instrument and combined that together with Pioneer observations at VLTI. And so these we have 7 separate nights of data spanning a period of less than 2 months. 2 of the nights, July 20th and June 9th, we have contemporaneous observations with both CHARA and VLTI. And if we just examine those 2 nights of June 9th and July 20th, 2019, if you just look at the visibility curves, you see that they have changed quite significantly between these 2 epochs. And if we put this data together with the higher sensitivity, we kind of see this easy plain Gaussian shape that we saw in the 2018 paper, where this is 10 years of data all put together. So you can see that if you've combined this data, you've smeared out a lot of your information that's useful. So what we've done here is taken this new data set and looking for temporal variations with geometric modeling. So using the PMOI red code by Antoine Morand, which is available on GitHub. And this code allows the definition of any number of components with custom radio profiles, projections, and then sinusoidal variation. And importantly, this code allows the positions of different components to depend on time. And so fitting a number of static models where things don't vary with time doesn't work. But I'll show a few models where we seem to be seeing evidence now for a moving structure. And so I'm plotting on the upper right the visibility with the same color scheme for the different nights of data, and then the closure phases here on the bottom. And as you can see that at longer baselines, we have very large closure phases getting up to nearly 40 degrees. And then I'll just play this video. So as the source is moving, the circle points here that are moving are showing what the visibility and closure phase would look like if you were to look at this model at that particular time. And we are able to better reconstruct or match these observations than with a static model. And then we do this again. So I'm showing a second disk model. So we've done this for a number of different distributions for the primary disk source. In all of these models, we recover this 25.1 day orbital period, starting at very similar position angles. And this seems to be consistent across a large number of different models that we try. So much the same as the disk orientation seems to remain consistent across different epochs as well. So overall, there is a lot of structure in the closure phases that we're not able to capture with these sorts of simple geometrical models. And so here I just kind of show a chi-square grid for a number of different periods and starting position angles for this moving disk feature. And again, so these are for the 2 different models that I showed, and we recover the same period and very close starting position for both of these. Yeah, so we recover this feature orbiting clockwise, so in the same direction as the outer disk's motion is. The period is consistent with Keplerian motion at where we expect the sublimation radius to be, and we see the center of the emission of the moving feature to be also roughly around the astrosilicate dust sublimation radius. And so if we do have some feature, so that's puffing up the disk in a certain region, then we can, this would be a nice way to explain the moving shadows that we see on the large-scale disk. And then finally, now that we add this complexity with this additional component that seems to be contributing about 10% of the entire flux in the H-band, we can't reliably be able to say how filled in the region interior to the dust sublimation radius is with the interferometric data and the modeling tools we have available at this time. So just kind of looking forward into the future, in order to really get a grip on what is happening, in order to be able to image this temporal variation, we'll need to have higher cadence observations together, combining data again with VLTI and Chara, VLTI giving those critical shorter baseline information, and then Chara nights getting the long baseline information. And then currently image reconstruction codes are still built in with this assumption that the disk is static. And so having some sort of smooth way to consider temporal variation across subsequent data sets will be the next thing that will need to be done on that front. I'll put that back up, and thank you.
Thank you very much, Benjamin, for the talk. Do we have any questions? Yes, got a few. I'll start down here. Yeah.
Hi, thanks. Thanks. That's a really very nice result. Very impressed. I was going to ask about you mentioned the 25.1 day orbital period was a consistent feature when you tried different sorts of distributions of flux. That period always came out.
Yes.
So that sounds very robust. How robust was the location or the radius of it?
The radius was more or less consistent. It's hard to tell. So I modeled the motion of the feature as a simple Gaussian, and so the size and location were probably consistent within about 10%, but based on kind of where if the model had an inner rim or if it was more diffuse for the disk, the exact location was around the place where you would expect the dust sublimation radius to be, but not 100% consistent.
Thanks. Jacques, any question?
Yep, Hayden, very nice work. I have a question because it seems that there are several local minimas for your period. So you choose the global minimum at 25 days. I was wondering if you check this period with existing Pioneer, Gravity, and Matisse observations, because maybe they don't have the angular resolution, but we see the asymmetry and we know the position angle of the asymmetry. And have you checked that with VLTI observations at other epochs to confirm this period?
Yeah, so to the first bit, I've looked at some of those other local minima that came out of the grid search for a period. And oftentimes those fits would put the moving feature at a very unphysical location where the motion would be many times Keplerian velocity. And for all of these fits, the most minimum spot was at this 25.1 day period. In terms of looking at data from other instruments, it would be a fantastic thing to do. Unfortunately, usually the time between when observations are taken is too long. So if you have observations taken, I mean, the source is moving, on 14 degrees a day, more or less. And so if you have observations 2 weeks apart at a very different time than these observations in 2019, it's a bit more dicey to compare.
Okay, but you confirm that the period is compatible with Keplerian orbital period with the mass of central star. That so the 25 days at this radius is compatible with Keplerian.
Yeah, it's about 95% Keplerian.
Okay.
At the sublimation radius.
Okay, thank you. And from online, Karine had a question.
It's first congratulations for these very nice results, and I have a few comments. First, I am fully supportive of combining Shara and VLTI observations. I think it's a good way to do. For the gravity observations, I think they are not so far in 2019 of the data that you have presented in your talk. And another comment is that you mentioned the complementarity in terms of baseline, but I think there is another one, is that with gravity, we can follow the gas across the bracket gamma line, and there will be a very interesting study to be done between the variability and the distribution of the dust and the potential variability in the gas.
Yeah.
Okay, is there any last questions? If not, thank you, Benjamin, again. Very nice talk.